Alright, welcome. In this video, we're going to be talking about polynomials. We're going to start in on our discussion of polynomials in earnest. We're going to talk about the zeros and inequalities related to polynomials. So first, we need to talk about what is a polynomial. Okay, so for us in our class, a polynomial is going to be something that starts off with some number plus some number of x's plus some number of x squareds, maybe plus some number of x to the thirds, and keeps going all the way up till some highest degree power, which we would say some number of x to the n's. Okay, you can't quite see all that. There we go. Okay, so this is what we would call an nth degree polynomial. Okay, but we probably need some more information here. I need to get this all on screen. All right, and what makes it nth degree is that the highest exponent I see is n. Now, I also need to point out a couple of other things. Notice that we're starting off with a0, and so it's just some number, and no power of x. That's okay, right? We can have some constant. But then after that, it has to only be whole number powers of x, like x to the first, x to the second, x to the third, no x to the 4.5 or anything like that. Okay, and then the other thing we need to see is real coefficients. So this a0, a1, a2, all the way up to an, these need to all be real coefficients. And that thing about real coefficients, that's actually going to be important for us when we go and discuss complex roots of polynomials, either in the next lesson or the lesson after. I can't remember. I know what we're talking about today. It's the zeros and the inequalities. Okay, so let me show you a couple of examples of things that aren't polynomials. All right, this thing right here, this is not a polynomial. F of x equals 3x squared plus 2 square root of x plus 4. And I'm going to say because if I was going to rewrite this as a power of x, that would be 2x to the 1/2 power. We would say not a polynomial because it has, a power of x that's not a whole and positive number. I've got another example for you. Right, and this, I guess it might be a lie to say that this is not a polynomial, but it's not going to be the type of polynomial we're interested in AP Precalculus because it doesn't have real coefficients. I see that I times x squared and that 4i there, those are not real numbers, okay? So this is not going to be a polynomial because of the non-real coefficients. All right, now that we've talked about what a polynomial is and isn't, we need to get into the discussion about the zeros so that we can then solve inequality problems. Okay, finding zeros of polynomials is something we've done a little bit so far in this class. We've done some factoring. We did it with just quadratics, but the same principle applies. And finding the zeros is going to be the tool we use to solve the inequalities. So let's just get right to it. We're going to start off with some factoring. In fact, all of the things in this lesson are going to be factorable. So we're going to start off with just some greatest common factor factoring. So f of x equals negative 9x to the 3 plus 12x to the 2. This is the type of thing we'll be able to factor by looking and saying, okay, what's common to both of these terms? Well, they both have at least 2 powers of x, so that's something I'm going to start with. I'm going to factor out an x squared. But then notice that negative 9 and 12 are both divisible by 3, so I'm going to factor out that 3. And so I think to myself, what would I multiply 3x squared by to get negative 9x to the 3? Well, definitely a negative to get that negative in there. 3 times negative 3 is negative 9, and then I would need one more x to make a total of 3 x's. And then I think, okay, what do I multiply 3x squared by to get 12x squared, and that would be positive 4. Okay, and if we're interested in finding zeros, zeros are where y equals 0. Okay, y is f of x. We're just going to set this thing equal to 0. And that's why we're interested in factoring, just to remind you about the discussion we had, kind of at the beginning of the year in the first couple of weeks, is that we like to factor because we want to use the zero product property. Okay, if two things are multiplied together to equal 0, like this 3x squared times the negative 3x plus 4 are, then it's got to be the case that one of them is 0. So it's either going to be the case that 3x squared is equal to 0, and that would only happen when x was equal to 0, or maybe negative 3x plus 4 was equal to 0, and that would be happening when x was looking like 4/3, yeah. Okay. And that one, I know that one's easy to make an error on, so I thought that one we could look at what we put in there for x. It's going to be something divided by 3, so that when I multiply it by 3, I get 4. Or if you want to subtract 4 and divide by negative 3, you be my guest. Okay, so those are our solutions. Now, later on, even today, we are going to notice that because, let me see what we got here. Because we had the 3x squared here, and that factor of x appeared twice, this x equals 0 is something that we're going to call a double root. And root, 0, x-intercept, all the same thing here. Okay, so now what I would like for you to do is try to do the one on the right. Do g of x on your own, factor out the greatest common factor, find the zeros by factoring, check your work against mine, because I'm going to bring it up here in a couple seconds. All right, there you have it. So I factored out the greatest common factor, which was 4x to the 3. I was left with a 4x and a positive 3, and I set each of those factors equal to 0. Either 4x cubed equals 0, and that can only happen when x is 0, or 4x plus 3 is equal to 0, and that can only happen when x is negative 3/4, and those are our zeros. And just like before, I could probably go ahead and say that x equals 0. In this case, is a triple root because I'm seeing 3 copies of x in the factored form, but we'll talk more about that here in a couple minutes. No, let's do another factoring type. Let's do some difference of two squares. So these two are going to have like a greatest common factor and then a difference of two squares. I'm going to do the one on the left, and again, I'm going to have you do the one on the right just to make sure you know what you're doing here. Okay, so I'm going to look at this, and if I'm interested in finding the zeros, I'm going to set the thing to 0. And I'm going to say what's common to both of these things. Okay, definitely the even number. 2 and 50 are both even, so I'm going to factor out a 2. I've got at least 3 powers of x on both terms. But me personally, I don't like factoring when the leading term is negative, so I'm going to also factor out the negative. Okay, and you don't have to do this, but I think that it'll make our job a little bit easier. I say to myself, what do I multiply negative 2x cubed? I didn't get negative 2x to the 5th. That would be 2 powers of x. And then what do I multiply negative 2x cubed by to get positive 50x to the 3? That would be a negative 25. Okay. And then we look at the x squared minus 25, and maybe we remember, okay, difference of two squares, a squared minus b squared is a plus b, a minus b. Or maybe we're saying to ourselves, what are two numbers that multiply to negative 25 and add to 0 because there's no x term in the middle? Either way, we're going to get negative 5 and positive 5. So we're going to say 0 equals negative 2x cubed multiplied by x plus 5 times x minus 5. And then from here, I'm going to go on and I'm going to say, all right, well, either negative 2x cubed is equal to 0. That would only happen when x was 0. Maybe x plus 5 was equal to 0, and that would be where x was negative 5. Or maybe x minus 5 equaled 0, and that would be where x was equal to positive 5. Okay, but that's going to be those are going to be my zeros. Okay, and it's still hardly visible to you. Okay. Now, you try it on your own on G with video paused, check your answers against mine, which are going to pop up in 3 or 4 seconds. All right, there you go. Now, I wanted to show you a different approach on this one. I don't want you to, watch this video and then think, okay, there's only one way to do this stuff, because there's always more than one way to do this stuff. I wanted to point out that x squared minus 9, we can factor that into x plus 3, x minus 3 if we like, but we can also just directly solve on that factor. If we've got it isolated down to something we can solve, we can say, okay, either 4x squared equals 0 or x squared minus 9 equals 0. And we can solve that by adding 9 to both sides and taking the square root of both sides. Now, taking the square root of both sides, that will incur a plus or minus, but that's where we see the two roots that we would have seen had we factored with difference of two squares. So it's all the same is what I'm saying. It doesn't really matter how you do it. All right, now let's move on and try another factoring type. So greatest common factor followed by, like a kind of a pretty standard quadratic. Right, so I'm going to look for the greatest common factor here. I've got 4x to the 3 minus 12x to the 2 and negative 72x, and I'm going to try to pull out at least that x and probably also the 4. Okay, and if you're sitting there thinking like, oh, I'm going to have trouble dividing 72 by 4, that's okay. I've got something for you. I'm also the type of person that doesn't just exactly know what 72 divided by 4 is off the top of his head. But what I can do is I can divide in half twice, and that's what dividing by 4 is, dividing by half, or dividing in half and then dividing in half again. Half of 72 is 36, and half of 36 is 18, and I'm good there. I don't know, I just never made that connection before this morning, I guess. And so this is going to be x squared minus 3x minus 18. And then that thing on the inside of the parentheses, this is, that's what we're talking about when we say a quadratic. And we're just going to factor this the old-fashioned way, looking for two numbers that multiply to negative 18 while adding to negative 3. And that's going to be somehow 6 and 3. So thinking x minus 6, x plus 3. Right. So now I'm going to give myself a little more room to work here and point something out. This 4x, that's just going to give me x equals 0. And if I write it out as 4x equals 0, that means x equals 0. It's pretty obvious, but it's very easy to look at that 4 and think that that needs to contribute to 0 as well. But it always comes from each of the factors equaling 0. That's where our solutions come from. And if you look at 4 as one of the factors, 4 can never equal 0, so that's why it's never contributing a solution, that little constant on the outside. Okay, so we say either 4x equals 0, and that would be where x was 0. We could say x minus 6 could be 0, and that would be x equaling 6. Or we could say x plus 3 equals 0, and that would happen when x was negative 3. And you know, there's another one of these, but I think I'm going to skip it in the interest of time because this is the type of factoring I know you're already good at. You know, if you made it to me this far, it's because you can find two numbers and multiply this and add to that. So let's keep it moving. And you know I couldn't just like sit here and give you all the factoring types without giving you one where the leading coefficient of the quadratic wasn't 1. So let's go ahead and do that now, and let me remind you of how, you know, what my preferred strategy is for this. But again, if you got a better or a way that you think is better to factor, as long as you're producing the correct factors, I'm in favor of that. I think you should factor or do any of this stuff the way that you see, the way that it makes sense to you. Okay, now because I'm over here recording a video to try to convince a large number of people at the same time of how we factor these things with a leading coefficient that isn't 1, I'm going to do it the most systematic way I know, which is by splitting up the middle term. So let's just get to it. All right, so like all the rest of these, this one's got a greatest common factor, and I'll talk a little bit more about why we made all of these have a greatest common factor here in a second. Negative 4x to the 3, positive 10x to the 2, plus 24x. So I'm going to factor out, I already said once, I don't like when my leading coefficient is negative, so I'm going to factor out a negative 4. No, I made this mistake twice in class. I cannot factor the 4 out because 4 doesn't divide 10 cleanly. I'm going to need to divide out a 2. So I'm going to factor out a negative 2 and 1 power of x. And then I'll be left with 2x squared, negative 5x, and negative 12. Yeah. Okay, and then just to remind you, what I'm going to do is I'm going to say, all right, I need to find two numbers that multiply to the product of these two. So I'm looking for two numbers that multiply to 2 times negative 12 is negative 24. So I'll call them u and v. So u times v equals negative 24. And then on the other hand, those two numbers need to add up to that negative 5 right here. So I'm going to just go down here and say I'm looking for two numbers that multiply to negative 24 while adding to negative 5. Okay, so factors of 24, 12 and 2, no. 24 and 1, no. 8 and 3, yes, here we go. All right, so I'm going to need one to be negative and the other one to be positive for them to multiply to negative 24. And if it's going to add to negative 5, I need the larger one to be negative, so I need negative 8 and positive 3. So I'm going to say negative 8 and 3. And then what I'm going to do is I'm going to split up that middle term and copy down the rest of the stuff that I have. So negative 5x turning into a negative 8x and a positive 3x, you know, like right here and there. And then still subtracting 12. Okay. And then I'm going to take this a little bit further and, you know, factor out of the first two things. Okay, what's common to 2x squared and negative 8x? A 2 and an x. I'm left with an x minus 4. And then 3x and negative 12, there's a 3 common to those. And then I'm left with an x minus 4, which is exactly what's supposed to happen because I need to factor out that x minus 4. So negative 2x times x minus 4, and then I'm left with a 2x plus 3. That's going to equal 0. So now I've got my factors. Kind of run out of room, so either negative 2x equals 0, and that only happens when x is 0. You can divide both sides by negative 2, or just think about it. We could have x minus 4 equaling 0, and that happens when x is equal to 4. Or we could have 2x plus 3 equals 0. That would happen when 2x was negative 3 and x was negative 3 halves. Okay, so I'm going to say my solutions are x equals 0, x equals 4, and x equals negative 3 divided by 2. And that's going to be our one daily factoring with a leading coefficient that isn't 1. I'm not going to make you do another one. And now, if you're interested, there's another one in the notes book, and you should definitely do that for practice. But that's not going to be the biggest focus here in AP Pre-Cal. And the reason I know this is, I've read the AP Precalculus course and exam description, and I just opened it up for you and I searched the word factoring. Now, this is the thing that I'm looking for, and I think these are the only mentions of the word factoring outside of in topic 1.5. Okay, in this topic, which is what we're talking about here, polynomial functions and their zeros, factoring polynomials without technology is limited to a greatest common factor and the rules for quadratics, which means we don't need to do cubic group and factor for terms with parallelism. We don't need that in this class. Okay. I also say the rules for quadratics, that does include what we just did with the leading coefficient not being 1. But the vast majority of them I would expect will be pretty easily factored, and plenty of greatest common factor. And the reason we emphasize that is because it was explicitly mentioned in the course description, because we want you to be ready for that. And so I could foresee a lot of greatest common factor, and like the ones we're doing, occasionally leading coefficient might not be 1 after everything's factored out, but for the most part I would expect them to be. Next, we're going to need to talk about multiplicities of zeros. And this, I know, is something that we've talked about in Algebra 2, but I want to re-emphasize it because it's going to be really important to our discussion here today. Okay, so reading to you from the course description, I don't need to show you this. If a factor is repeated n times in the fully factored version of the polynomial, the corresponding zero of that polynomial has multiplicity n. That's the definition they're giving in AP Precalculus. It's essential knowledge 1.5.A.2. Okay, really what it's getting at is the fundamental theorem of algebra, which is something we're going to see a little bit of evidence of today, but we'll see more of next time when we talk about complex zeros. Okay, so let me just show you with an example here. So suppose we're given a fully factored polynomial. It's x squared times x minus 5 cubed times x minus 4. Okay. I'm going to rewrite this. I'm going to rewrite this in a way that it will make this hopefully as obvious as possible. All right, and I copied the example wrong. It was supposed to be x plus 4 for a good reason. I don't know if you're working on the original version of the notes book, I did change it to x minus 5 to the third power because I don't want the multiplicity to be the same as the x value of the root. Okay, I don't want any kind of confusion here. I'm also going to mark this as x minus negative 4 to the first power. And the reason I'm doing this is I want us to be able to easily see where the zeros are coming from and where the multiplicities are coming from. So the zeros, those are the x values that we're, probably pretty used to reading out of the factored form of the polynomial. Those are going to be 0, 5, and negative 4. Hold on, my highlightering was not the best there. All right, that's much better. So now you can see that my zeros are 0, 5, and negative 4, these x values that correspond to f of x equaling 0. Okay, but then the multiplicities, I'm going to go grab those from the exponents, the number of times the factor is repeated. Okay, so the multiplicity for the 0 at x equals 0 is going to be 2. The multiplicity for the 0 at x equals 5 is going to be 3. And the multiplicity of x equals negative 4 is going to be 1. Okay, for multiplicity 1, we oftentimes call that a single root. For 2, we would call that a double root. And 3, we would call it a triple root. All right, here's one for you to try on your own. So I added a little something else to this one that wasn't there before. I also changed it a little bit from what's on the notes book because I didn't think the last factor wasn't really adding anything to the problem. So I want you to try this on your own. Identify the zeros and their corresponding multiplicities. Check your answer against mine, which is going to pop up in a couple of seconds. All right, there you go. So x equals negative 1 is going to have multiplicity 2 because the x plus 1 squared, and x equals positive 2 has multiplicity 4 because of the x minus 2 to the fourth power. Notice how that negative 3 did not contribute anything. I'm not going to have x equals 0 being a root. That's a common error. I'm not going to have x equals negative 3 being a root either. Okay, that factored out negative 3 really affects the shape of the graph for reasons that we've actually talked about a little bit so far in this class, but if you're not seeing, I would be happy to show you again in the future. Okay, so that's the deal with multiplicities. Let's go ahead and use these on solving some inequalities. All right, so suppose you have factored up a polynomial and you factored it into this form, and you're interested in where f of x is less than 0. Okay, and I'm going to actually write that out. All right, so this is exactly the type of problem that we solved in the previous chapter with the use of a calculator, but we're going to need to do these for a polynomial without the use of a calculator. Now, I am also very confident that this is a multiple choice question, and I'm not going to get into why based on the course description, but they're prescriptive in the free response. They're telling you what's going to be on the free response, and this is not one of those things, therefore it has to be multiple choice. And you already know how to do it without a calculator, with a calculator, so we're going to focus on no calculator here. What we're going to do is we're going to start with an x-axis, and we're going to label that x-axis with the zeros and their corresponding multiplicities. All right, so there we go. I've got an x-axis. I have thrown down my zeros, x equals 0, x equals 4, and x equals -2. Now, I do need to remind myself that x equals 4 is going to be a double root, whereas the other two are going to be single roots because they're only appearing once. So it says in the notebook, so a student found that f of 1 is greater than 0. Okay, so that's what we're doing, like testing a value in between each of the zeros. So I'm going to just put x equals 1 right there. But I'm going to show you how the student figured out that f of 1 was greater than 0. What they did was they plugged in 1 for x, and that's going to be 1, times 1 minus 4 is -3 squared, times 1 plus 2 is +3. And I'm not as concerned with the fact that this is equal to +27 as I am concerned with the fact that this is a positive number. So what I'm going to do is I'm going to say, all right, 1, that's a positive number, multiplied by -3 squared, that's also a positive number, and 3, that's a positive number. So I've got 3 positives multiplying together, and that's going to give me positive. So we put a little plus sign there at x equals 1. But now I want you to think, is it possible for f to have gone negative by the time we hit x equals 2 or x equals 3? And the answer is no, because the only place that a polynomial can go from positive to negative is at a 0. And we've already written down our list of zeros, our complete list of zeros. There aren't any others out there that we don't know about, right? We've got them all written down on the number line. So if I found that f is positive at x equals 1, I actually know that f is positive for all x between 0 and 4. So I'm going to put, like a couple of more pluses in there, and I'm going to get rid of that arithmetic so I can do the same thing for the other subintervals. All right, next I'm going to move to the right, and there's nothing saying I couldn't start from the left or whatever. I just see, okay, let's pick a number bigger than 4. I'm going to choose 5, but you can choose 10, 100, a million, any number you want, just as long as it's greater than 4. Okay, and then I'm going to plug in to f. f of 5 is going to equal, well, that's going to be 5, which is a positive number. 5 minus 4 squared is 1 squared, that's a positive number. And 5 plus 2 is 7, that's also a positive number. Okay, so I've got positive times positive times positive, that is also a positive number. Okay, so I'm seeing all positive from 4 to infinity. Okay, then I'm going to, oh, whoops, I forgot to say that's a positive number. But we're just going to go in and clear that out so that we can go back here and say, all right, a number between -2 and 0 would be -1. Consider the same idea. -1 is a negative number. -1 minus 4 would be -5, but if I squared that, I'd have +25. So this is going to always be positive. And then -1 plus 2, that goes back positive. And a negative times 2 positives, well, that's going to be a negative number. So I've determined it's negative here, so I know it's negative all throughout that interval from -2 to 0. And then what I'm going to do, I'm going to choose one more test value. Maybe this time I'll choose -10. All right, so when I plug in x equals -10, that first x, that's -10, that's a negative number. -10 minus 4 is -14, but if I square it, that will become a positive number. And -10 plus 2 is -8. So I've got two negatives and a positive multiplying together to make a positive number. So I've got positive all throughout this interval. And if I go in and I just actually clear this out, now I've got some information about the function. Okay. In the future, you won't see me writing 3 plus signs, 3 minus signs. That's overkill. I'll just write 1 plus sign and 1 minus sign, or maybe write positive and negative to indicate that that's the behavior of the function over that entire interval. Okay. Now, if I'm interested in where f is less than 0, well, that's when f is a negative number. So that's going to be right here between -2 and 0. So -2 is less than x is less than 0. Okay, now that's great. We just solved our first polynomial inequality, and that's how we're going to be wanting to solve inequalities throughout this course if they've got more than one power of x in them at the same time, which this one certainly does. Okay, there's another message I need for you to get, though, and that's what's happening to the signs of this polynomial at a single root versus at a double root. So think about what's different about x equals -2 and x equals 0 versus x equals 4. Are you seeing it? Are you seeing the fact that at x equals 4, I went from positive to positive? The sign didn't change. Whereas at x equals -2 and x equals 0, the signs did change. So in general, when we're making these sign charts, and that's what we're going to call this thing that I just did up above. It's not a graph. Okay, it's a sign chart. With these sign charts, if we're looking at an even multiplicity, oh no, I just wrote it backwards. Oh goodness. All right, well, it's fixed now and is not worth going back and re-recording the video, and I'm not advanced enough with my video recording capabilities to like go in and remove that part of the video with the erroneous statement, but I just really want to emphasize an even multiplicity. That's where we're not seeing a sign change. So we had a balance on the graph in a previous course, and we will see that here, just not today as much. And with an odd multiplicity, the sign will change like it did at -2 and 0. Okay, so just really want to emphasize even multiplicity doesn't change signs. Odd multiplicity, yes, there's going to be a sign change. Let's do a few more of these. I think I'm going to do 2 more for you, and then I'm going to have you do 2 on your own, and I think that'll be enough for the inequalities. There's a lot on the notes book, and you can keep doing those and come talk to me about them if you need extra practice. But we also need to talk about sketching some graphs here, so I'm already seeing this video is going to be about 30 minutes or maybe even longer, and I don't want that. I hate when that happens, but this is a long lesson, and it's relatively important to what we're going to do. So I'm going to draw in an x-axis. I'm going to label my roots. So I've got x squared, that's x equals 0, which is a double root, which I think is worth writing there. But at x equaling 3, x equaling -2, those are also roots, but they're single roots. What we're going to do now is we're just going to test one point and use that fact about the multiplicity to fill out the rest of the sign chart. So it should go much faster, I hope. Okay, so let's test our point x equals 1. Sure, it's between 0 and 3. And I'll actually show you another one here in a minute that you would be wise to choose from the far edges. And that was actually an idea from a student in my class. So 448, you were really thinking this morning, and that was a much better suggestion than what I was going to offer. But we'll do that one here in a couple minutes. Okay, at x equals 1, I'm going to choose that point right here. I've got x squared is a positive number. 1 minus 3 is a negative number, and 1 plus 2 is a positive number, so I'm ending up with a negative product. So I'm going to write in negative there. Okay, well, x equals 3 is a single root, and I am going to see a sign change at a single root, so it's going to change from negative to positive there. Okay. X equals 0 is a double root, so I'm not going to see a change in the sign here, so it needs to be negative again. And then x equals -2 is a single root, so it will change signs as I move to the left, and I'll just say, okay, that's going to be positive. And changing versus not changing, and we only need one test point. Now, if I go and I get rid of the arithmetic, I'm going to be able to figure out, okay, less than or equal to 0, or equal to 0 here, and there, and here. If it's less than or equal to 0, well, less than 0 happened through here. Equal to 0 happened at the endpoints and at x equals 0. So I'm going to say -2 is less than or equal to x is less than or equal to 3. If you wanted to write this in an interval notation and say, okay, -2 up to 3, including both endpoints, you'd be welcome to do that. Okay, so there we are. We solved another polynomial inequality. All right, so here's another one. And this is the one I was talking about where, if I wasn't careful about my test point, I'm going to need to be choosing a number, between 1 and 2. Well, there's no whole numbers between 1 and 2. So in the past, I'd always just been like, oh, well, let's try 1.5. Okay, but like I said, a particularly thoughtful student suggested maybe I try x equals 4 instead to make the arithmetic easier on myself. Now, I think that student knew that I sometimes have trouble with arithmetic. So that was, particularly considerate. But I really like this idea because I like plugging in whole numbers. I don't want to deal with the halves. If I have to, I will, but we don't, right? Because we can always choose one on the very outsides, right? Something really positive or really negative, or just outside the subintervals. All right, so x equals 4. X is positive. X minus 1 is a positive number, and I square it, so it's definitely going to be positive. X minus 2 is 2 cubed, that's a positive number, and x minus 3 to the 4th, that's going to be 1 to the 4th is a positive number. All right, so I've got positive out here. And now I need to be considering the multiplicities of my roots. Okay, 3 has multiplicity 4, which is even. So I'm not going to see a sign change, right? It was positive and it will stay positive. X equals 2 has an odd multiplicity, so I will see a sign change. X equals 1, even multiplicity. Okay, so in this case, the sign will not change, it'll stay negative. And then at x equals 0, that was a single root. So single, that's the multiplicity 1, that's an odd number, I will see a sign change. All right, so I'm interested in where this thing is greater than or equal to 0. Well, it's definitely greater than 0 all throughout here, where it's positive. It's equal to 0 at each of these roots. Oh, and it's positive again over here. So I've definitely got x is less than or equal to 0, and I've got x is greater than or equal to 2. But I should also probably report x equals 1 as part of my solution, because that's a place where that polynomial is equal to 0. Okay, and that one had a little something different. I think I'm going to do one more for you that involves actually factoring. So we're going to solve this polynomial inequality here, same as we did before with a sign chart, but it wasn't given to us already factored. So we need to, kind of merge these two skills. We need to start with some factoring and then do our sign chart analysis. So I'm going to say what's common to all of these. I've got an x in all of them, so I'm going to factor out the x. And then I'm left with x squared plus 8x plus 16. Okay, that itself is factorable. I'm looking for two numbers that multiply to 16 and add to 8, and that's going to be 4 and 4. Okay, so I'm interested in where this is greater than 0, and if I factor, I'm going to get x plus 4 and x plus 4, so I'm going to write that as x plus 4 squared. Okay, and so I'm going to actually cut out this middle row and move this up so I have more space to work. And I'll get myself an x-axis, and I'm going to label the roots. Okay, I've got x equaling 0 and x equaling negative 4. Now, x equals negative 4 is a double root, so I will need to be careful there. Remember that there's not going to be a sign change on this polynomial at x equals negative 4. I'm going to test a value. I'll test x equals 1 right here. Okay, and I'm going to want to go with a factored version. Now, if you can tell looking at the original unfactored that 1 plus 8 plus 16 is going to be a positive number, good for you, that's fine. But it's going to be easiest for us in general to be working off the factored version when we're doing these test points. Okay, so x equals 1 is positive times 5 squared is definitely positive, so I've got positive over here. Okay. X equals 0 is a single root, a root with odd multiplicity, meaning that there is a sign change. So I'll write negative there. You don't have to just write a plus sign or a minus sign. You can do whatever you want. Okay, and at a double root, we're not going to see a sign change, so this is also going to be negative. Okay, and so if I'm interested in where this is greater than 0, well, it's equal to 0 here, and it's positive all throughout there, so this is going to be where x is greater than 0. That'll be the solution to this inequality. All right, now the last thing I've got for you is sketching graphs. But I know that the notes book goes forward and gives you new examples, and those would be good ones to practice on. But what I want to do is I want to only work with the sign charts that we've already made in this video. So I'm going to go back and I'm going to bring in all of these sign charts that we'd already made and use that to help us sketch a graph. All right, so most recently we solved x to the 3 plus 8x squared plus 16x greater than 0. Okay. Now, who cares about greater than or less than 0 right now, except for, making a graph? I'm going to get this out of here, I'm going to get that out of here too, but I'm going to leave the negative and positive stuff. Okay, what I'm going to say is, all right, maybe we're just going to call this f of x. Okay. Well, we've got all the information we need. We've got the intercepts, the x-intercepts, the roots here and there. Okay. And, well, if it's going to be negative, between negative 4 and 0, well, it'd probably look something like that. Now, I think we can do a little bit better. If the graph is negative, the one thing that you don't have is the end behavior of the polynomial, which we're going to talk about next time. But you know that these things, they're going to either go up to infinity or negative infinity. And so it's telling us if it's negative forever to the left of negative 4, well, what I'm going to do is I'm going to go down to negative infinity. So that means the graph's going to come up like this, and since it's going from negative to negative, I'm going to hit a little relative maximum there. Right? We've got that vocabulary now, so we can say that. It bounces, as you saw that in last year or something. And then we're seeing a sign change here at x equals 0. and we're going to, just kind of continue going up just like that. Okay, so that's going to be a pretty decent sketch. If I wanted to talk about y-intercept, which I kind of do, I draw in a y-axis. Whoops, that could have been better. Like that. And then all of a sudden I've got my y-intercept labeled as well. Okay, so let's do a couple more of these. All right, now another graph that we could make would be the graph of this function. First thing I might ask, I asked this one in class kind of just for fun, but I got some good answers and some good discussion after it. So I'm going to ask you, if this is g, what's the degree of g? Okay, I'll just tell you, it's degree 10, and so it would be the highest exponent if I was to multiply out all of these things. Now, we're not going to be doing that, right? There's no need for that. We can just envision what would happen if I took x minus 2 to the third power. I'm going to have x to the third and some other stuff. And I will talk more about that. I think that's the fourth lesson in this unit, is what to do when you have to take a binomial to a higher order power. But our advice is going to be just be brave. What I was going to say about this is g is degree 10. We're not really worried about the end behavior of this thing. But if it's coming from a positive place and then it's going to go negative, it's probably going to look like that. Okay, and then it's going to be negative again after that. Then I have a sign change, and then it goes back to 0 and back to being positive. So that's going to be what the sketch of the graph would look like. And again, if I wanted to write in a y-axis to make this like a really nice sketch, I could do that here, and I would have my y-intercept labeled. Oh, see, got cat action in the background there. All right, and then the last one I got for you, we could go all the way back and we could do all of them, but I think this will be enough, is going to be this one. We're going to go in and we're going to call this, I don't know, maybe capital F of x, and then we're going to go in and say, all right, the graph was positive, and then it became negative, so we're changing signs. And then it was negative again, and then positive after that. And that's going to be the type of sketch we need. I didn't even look to see if there were any triple roots in any of these that I've sketched. I'm pretty sure there was on the last one, and then I went and erased it. But we're not worried about the fact that the graph is hesitant near the point of a triple root. Not yet. We will be, I think, next time. But we're going to have more language for that, more discussion on it. That's going to be all. Really, all we're concerned with today is finding the zeros and solving the inequalities. The sketches, that's just a preview of what's to come. So that's going to be all for this video. Thanks for watching.